Madam, shall we start the session?
Okay, thanks. Hope I am audible, right?
Yes, sir, you are audible, sir.
Okay. Good afternoon, everyone. Let's start to today's session. We'll go for the learn about Ansys Fluent meshing and the meshing in the Ansys workbench, right? Yesterday we learned about the geometry cleanup in and geometry creation in SpaceClaim. From there, today we'll move further to mesh the cleanup geometry in Ansys Fluent as well as Ansys workbench. Okay, so let's go there. Let's start with the SpaceClaim. My screen is visible, right, to everyone?
Yes, sir.
Okay, thank you. Let's start the SpaceClaim. Okay, this is a SpaceClaim window. Yesterday we have cleaned up some geometry and saved it. Let's start it. So let's start with the simple geometry. So we have two things: cubes with pipe and cubes. Yesterday we did it, right? Okay. Before moving, let's we have to mesh this cube. So already the mesh is generated. Sorry, the geometry is generated. Things are named. So and this is saved in the directory. This is natural convection. Okay, we'll mesh this geometry. We'll show it how to mesh this geometry in the Ansys Fluent as well as Workbench. Let's first go by the mesh by Ansys Fluent. Okay, so let's to open that, just go over here. Just you can put it Fluent 2011, 12, whatever the version. You can open it right now. Okay, when you are opening, it will ask for you two options, whether you are going for the solution, you are going for the meshing. Okay, if your mesh is ready, then you can proceed for the solution. If not, then choose meshing, right? Then give the directory in which you have the your geometry file. Suppose this is my currently directory location in which I have my geometry file. So go over here, put it geometry file. Okay, then you can choose whether you have a serial meshing or you have a parallel meshing kind of thing. So I can choose, suppose I need two processor for meshing. Okay, so you can choose it. Okay, it's a double precision. If you want to save your mesh information in a single precision or double precision, like coordinate, surface area, etc., you can choose it double precision. Let's go to meshing. Okay, this is the Ansys Fluent Mesa home, right? This is by default, it will show the workflow. Let's come to the outline view, right? So already you have a clean SpaceClaim geometry, right? Then once you come to the Ansys Fluent Mesa, just go over here, file, then you have to import the geometry. Then come under the import, there are a lot of options. Suppose you have prepared a surface mesh in the just like hypermesh or some other software, you can save it on Astron. Those you can import it over here, right? If you have used earlier Gambit neutral format or CGNS format, those things you can import over here. But here our geometry is in CAD, right? Go over CAD. Okay, then it has the option to you import a single file. Yes, we don't have multiple file right now. Then go and choose the file. Okay, this is my file, simple cube is my file. Let's choose the file cube. Okay, then it will ask you the unit length. Okay, the unit in which SpaceClaim works is normally mm. So while creating the geometry, we have choose the dimension like 500 mm, 400 mm, like that. So unit is mm over here, not meter. Okay, but in the solver by default unit is meter. So that's why you need conversion. I will tell during the solver setup, I will tell how to do that conversion. Okay, then after doing this, it will ask you other two options, tessellation or the CFD surface mesh. Normally what will happen when we import our geometry to the CFD solver? Normally the CFD solver, they do what, CFD mesher, they do the surface meshing, right? Either they do the CAD faceting, means they will bring a very big element, possible element, or they will prepare a surface mesh of your closing surface, okay, with prescribed size. Okay, so let's choose surface mesh. Okay, then once you choose surface mesh, then it will ask you to choose minimum size and maximum size and growth. Okay, suppose we have taken a cube of 500 millimeter, right? Let's choose the minimum size is 2 millimeter, maximum size I can 10 millimeter. Okay, growth is around 1.2, right? This is the curvature. If you want proximity, you can catch it and put it proximity and around 1 or 2. This will number of elements for the cells, number of cells for the gap or the edge of the curve. So this proximity always choose. It will show the proximity to the face and edge and all, but to choose it proximity to the edges, right? Then option. So if you have a multiple parts, then choose, there are a lot of options. The extract feature, extract angle is around 40 degree. You can, if you some features is not captured, you can reduce it to 15 degree, 20 degree, but for the timing, let's keep it default. Okay, then try to import the mesh. Let's see. Now my surface meshing is done and my geometry is imported to the Fluent. Okay, how to see it? Go over here, mesh object. Okay, the cube fluid here in space claim, I have given the name. Okay, cube fluid, you can see cube fluid, it's the object is coming under the cube fluid, it is coming. Now see what object is coming. Okay, draw. Let's to see all the surface mesh. Let's first fit it over here. Okay, this is my geometry. Now nothing is visible because the it's white. So to see the elements and all, three faces, multi faces, and face edges. Now you can see my cube, whatever I have prepared, they have already imported as a surface mesh to the Ansys Fluent mesh, right? You can see it over here. Then it's just surface mesh. It's not yet volume mesh. If you want, we can change a lot of meshing parameters in the Fluent mesher to customize the mesh and proceed towards the volume mesh. To generate a volume mesh, the first thing is required is a good surface mesh, right? So I just give some rough import setting. Based on that, the surface mesh is prepared and it's imported to Fluent, right? Then compute, you have a single volumetric region or you have a multiple volumetric region. Okay, so just go for there. Just first check the quality of the surface mesh. Okay, surface mesh, if there is some free face or so there is some opening, there is some leakage, all those things you can check it over here, and also you can, all the things you can have rectify over here. How to do that? Let's go to the diagnostic. Okay, connectivity and quality. Okay, so now if you go, if you find some free faces, if you mark there is no free faces. Okay, if you find there are some intersection or some element are piercing, no, everything is 0 0 means your mesh is good, right? So let's go find out some of the thing. Quality, so let's find out what's the quality. Skewness, let's put it around 0.7. Check if there is a skewed element or not. I'll come to the theoretical part, what this skewness is, what this uh, uh, other the quality criteria, just like aspect ratio, etc. I will come to the theory part. Give me some time. So for the timing, just assume it's a these are some criteria they are prescribed to check the quality of the mesh. So skewness is something around 0.7 or 0.5 is okay. Let's check and mark if there is some skewed element. Nothing is skewed. Okay, then close. Now check the summary, means it will show how many elements are there. The maximum skewness is around 0.33. There are around 34,938 are my surface element, right? Then generate the volume region. Okay, compute. Once you do the computation, you can see the volumetric region is created, right? So in this volumetric region, you can see this here. Just go to reset view, draw. Now this is the volumetric region. You have one volumetric zone. Now it is created as volumetric region. So now default, if you see this volumetric region, by default it is solid. Okay. So you want this to be a fluid zone. How to do that? So now go over here. Okay. Then manage. Sorry, change type. Change type. Now it is by default solid. You can do it as fluid. Now you can see the fluid symbol. Now it is a fluid generation thing. So now suppose I want to do the volume mesh, right? This is my surface mesh is prepared. I found there is no problem in my surface mesh. I will go and show you if there is a faulty surface mesh, how to repair it. Okay, but for the timing, assume there is geometry is very clear. There is no defect in surface mesh, and it is closed, no free edge, no T edge. The maximum skewness is in the prescribed criteria. Now to proceed to the volumetric meshing. So let's volumetric meshing. Go to the cell zone, choose what auto mesh option. Okay, in this auto mesh option, there are a lot of options you can see in the tab that comes under the auto mesh option. First thing is prism layer. Okay, I hope already you have gone through the theory of the turbulence modeling, where you have come across the turbulence boundary layer, right? Sorry, the wall correction and the low Reynolds number model, etc. So normally what happens, the flow field, in the turbulent flow field, the dynamic viscosity doesn't play any important role, provided the flow is far away from the solid surface. Because if you move away from the solid surface, the turbulent eddy viscosity that predominant over the dynamic viscosity. So dynamic viscosity is not much important, because eddy viscosity is several thousand times more than the dynamic viscosity or the molecular viscosity. But if you come close to the vicinity of the solid wall, no more you can discard the presence of molecular viscosity. So close to the wall, the molecular viscosity predominant, that is called viscous sublayer, where the viscosity effect cannot be neglected. Then above the viscous sublayer, there is a buffer layer, then there is a log layer, there is a destructive layer or defect layer, a lot of things. So theoretically, hopefully you have gone through it, or Professor Andy Chan will cover those things about this turbulent flow near the solid surface. Okay, now to capture those viscous sublayer, okay, if you are solving a flow over a solid surfaces, so you need a very fine and uniform mesh near the solid surfaces. Normally there are two ways to deal with the flow across the solid boundary. One is the low Reynolds number method. One is the wall correction. Okay, what low Reynolds number method? In the low Reynolds number method, they resolve the viscous sublayer into number of grid, and they solve the entire Navier-Stokes equation in those region of the near the wall. That is called low Reynolds number model. And this uniform grid near the solid region, they are called the prism layer, right? Similarly, if you are going for the wall correction approach, instead of solving very number of prism layer adjacent to wall, they go to a bit higher y plus, more than 30, 40 or something. Then they generate the fast cell height. Okay, that is called the wall correction approach. Hopefully, theoretically, you will come across these things in the lecture. If not, Professor Andy Chan will cover this soon. So describing again the complete theories beyond the purview of this particular lecture. So just keep in mind, prism layer is something we are generating in the vicinity of the solid boundary for the uniform layer. These are the uniform layer to capture the viscous effect close to adjacent to the solid boundary. To then to generate the prism layer, what you do, then there is an option called boundary layer mesh. Okay, grow prism. Okay, let's choose scope means this again give you a kind of functionality to capture prism layer across a particular wall. If you want to develop a prism layer at a particular wall, if you don't want to develop a prism layer at a particular wall, this will give you the flexibility. Let's go to the scope, right? Then set. Okay, we have to choose where to generate the prism layer. First, give the prism layer name, just wall prism, something. I give it name wall. Here is a wall prism, right? Then how you set the prism layer? It's the aspect ratio, it's the uniform layer, it's the last ratio. A lot of other options are there. Let's choose it's the aspect ratio. Okay, aspect ratio means the prism layer surface length to the length in the vertical direction. Let's choose it default. Aspect ratio is 10. Number of prism layers, suppose you decided to 5, you can reduce it from number of prism layer 2, 3 to 8, 12, 20 as per the requirement. The growth rate is you put it something around 1.2 as per the requirement. You can change it. So ideally it's 1.1 is something we are using. So there is no hard and fast rule based upon the situation. So on the model of the turbulence, you can choose it something 1.01 to 1.1, 1.2, but again it's 1.1 is the best practice. Okay, then which object? If you have a multiple object, then this is the cube field. This is the geometry in which you want prism layer. If there is a something porous zone where you don't want prism layer, don't select it. Okay, scope to named region. Okay, means fluid region. Then grow on only on walls. You change it to selected phase zones. Means this will give you the functionality. Declare the prism layer in the wall you like it. Okay, let's go there. Let's say boundary to scope. If you go there, it will show all the boundaries that we have named in our space claim, right? We want prism layer at everywhere because these are all wall. So I just select everything. Okay, okay. Then growth option, you choose something, keep first layer offset by put it default. Okay. Now create that one. Now my wall prism is created. Okay. Now it is scoped. Then the volumetric mesh. There are multiple type of volumetric mesh, just like pyramid mesh. Then there is a tech mesh. There is a hex mesh. There is a poly mesh. There is a hex core poly mesh. Okay. Before going further to the meshing, let's have a look on the theoretical aspect of the mesh, so that we can understand what this mesh are really telling this poly or hex core poly mesh. Okay, let's give me a couple of minutes, go to some theoretical details. So okay, let's come. Let's check. I have somewhere. So any doubts so far? Any query? Any doubt or any query or not? Or we can proceed. Okay, thanks. So let's go to the meshing. So am I audible right now? Connection is okay?
Yes, sir. It's
Okay,
audible.
fine. Okay, fine. Hope my slides are visible, right? So let's put it presentation mode. Okay, so this is something called introduction to meshing. So normally people from mathematics or the engineering background are here. So let's have a simplified introduction to meshing. So normally if I ask you to find the area under this curve, right? What you will do? You will integrate this curve, okay, with the desired length. So x-axis from 0 to L. If I do from 0 to L and do the integration, okay, I will find the area that is covered under the curve if provided the analytical integration exists, right? If I have a function sine, cos, or some polynomial function, I can integrate it and get the area. Suppose this is an arbitrary function for which analytical integration doesn't exist, right? Then what we can do? We can, to find the area, we can do the numerical integration. Okay, numerical integration is nothing but the integration is replaced by summation with some weight factor, right? So to do that numerical integration, to find out the area under the curve, what we do? First, we have to break the area into a very small strip. Then we find the area of that strip and do the summation of that strip, just like f of x1, right? So if we bring it to very big structure of the strip like this, the area will be how much? The delta x, the strip width, into the length. The length is nothing but fx. At a particular x, it is showing the value is equal to fx, right? Then we approximate. If my delta x is very big, then my fx approximation is very bad, right? The fx is somehow here, supposed to be here, but I approximated because of the very high value of the delta x. I have assumed fx somewhere here, not here, right? So in that case, what we'll do, we have a lot of error will be generated, right? As we go on decreasing the width of the my strip, okay, taking small to small element of delta x, then we can see we here the delta x is more. Here we decrease the value of delta x. Here we further decrease the value of delta x, and here we have a very fine delta x, right? We can see as we go on decreasing the size of the delta x, the area under the curve is much more accurate, right? But at the same time, the computation cost will be increased. You have to compute such infinite line element and do the summation of those line element to find out the area under this curve. Here, if you go for a very high delta x value, you will get several 3 or 4 element, but again it comes with a numerical error. So we have to be trade-off between the very fine element and very coarse element, okay? Then somewhere in terms of the computational expensiveness and numerical accuracy. So somehow this is called good mesh. The concept of meshing is very similar. The method is called finite volume method. It's finite volume method. What exactly the word finite volume is telling? So when you are deriving any governing equation in fluid mechanics or in mathematical continuum mechanics, you are assuming limit delta x tends to 0, delta y tends to 0, delta z tends to 0, and deriving the governing equation. Here in the method, when it is derived, it is assumed not delta x tends to 0. It is assumed delta x is a small value. No matter how much small it is, it has some finite volume or it has some finite magnitude. That's why it is called finite volume method, right? So let's come the idea where it came to the meshing. So this is a famous painting. Okay, this is from the French philosopher called René Descartes. He is the 15th century French philosopher. The Cartesian geometry, what we are reading now, the Cartesian geometry is named after this René Descartes. What he find out easiest way to paint something. Okay, what he did, there you can see the lady is sleeping. Okay, he supposed to paint the picture. If he is not a professional painter like Leonardo da Vinci or something, it is very difficult to watch and paint it. So what he normally usually do, he just for a fun, this is published by some French magazine, he put a net, okay, between the object and the painter. Okay, then in the net there is small portion, or we can tell grid. Each grid he made some projection over here. he is looking through each grid how much portion is visible, and those he is reproducing, those portion he is reproducing in the same grid, right? At the end, when you are covering the entire grid, he supposed to reproduce the image what is seeing through the whole window or the slit, right? This is just a I can say this is satire kind of thing, but the exact idea of the CFD is to save. So what you do, we just a geometry, we split it into multiple small unit that called cell or grid. In each cell or grid, we solve the governing equation, then we integrate it over the entire volume to get the total phenomena over the total fluid domain. Okay. Then the problem is now we have know what is missing. Then what is again, just I told in the earlier side, we have to come to a trade-off between the mesh efficiency, the computational efficiency, and the quality, right? What are the quality? I will come. Okay. Then this is the mesh setup procedure. So there are a lot of things associated with the mesh, basically Ansys Fluent. So once you mesh some geometry, okay, there is the fundamental unit is called cell, right? This is the fundamental unit. This is the individual small volume that you will get after the meshing, right? There is something called edge, right? Each cell, they are associated by some cell faces, cell edges. There are some points that is called nodes, etc. Okay, if the face is a boundary face, then there is not more adjacent cell will be there. Okay, if this is a boundary face, there is not any adjacent cell here. There is only cell towards the fluid domain, right? So now let's come what is structured versus unstructured mesh. If the number of neighbors of a cell keeps on same, they remain same throughout the fluid domain, this is called structure mesh. Okay, this side is my structure mesh, means here the number of neighbors, any element you consider, okay, the number of neighbors remain same except the boundary one. Okay, here the boundary one number of neighbors is 1 2 3, right? So except the boundary is a element, any element you consider here 1 2 3 4, here 1 2 3 4, if they remain same, this is called a structure mesh. But if the number of neighbors keeps on changing, that is called a unstructured mesh. This is the basic terminology, structure and unstructured mesh. So here you check a mesh surface mesh element. So what is the number of neighbors? 1 2 3 4 5 6 7 8, right? So here you check a surface element. What is the number of my neighbors? 1 2 3 4 5 6 7, right? So here 8, here 7, means it's a unstructured mesh on this side. Normally in the commercial solver like Ansys Fluent or any other things, commercial solver like CD, Star CD or Star CCM. So the meshing of complex geometry, it is very difficult to prepare a structured mesh. Everything comes as a unstructured mesh, right? So let's come. So elements type, normally we have a two-dimensional view. We have a element of quadrilateral, that's a we call it quad element. We have a triangular element that we call a tria element. Then we have a polygonal element, right? Then this is for the 2D. In the three-dimensional version, we have a element called hexahedron, a cube kind of thing. This is called hexahedron. Hexahedron consists how much? 6 faces. This is hexahedron. Then there is a three-dimensional element called tetrahedron. We have 4 faces. This is coming tetrahedron. Then something called a prism. Okay, it has 5 faces. Okay, 1 2 3 4 5 faces. This is called prism. Then something called pyramid. Okay, this has 1 2 3 4 5 faces, right? Then there is a polyhedral, means it's more than 6 faces. This is called polyhedral, right? Then let's come. I am not going further to the theoretical details because it will make the session bore. So let's coming to the quality, some of the theoretical background of the quality. So when what is skewness? Normally the within a circle, if you have to draw a triangle, the triangle has to be equilateral, right? So it has to be the equilateral triangle defines the optimal cell size. But if your cell size is deviated from the equilateral triangle, but it is fitting inside some other circle, then the skewness can be checked for the triangular element by this way. Optimal cell size means the area of the equilateral triangle minus the cell size you have generated, that is the triangular cell, divided by cell size means the equilateral cell size. This will give you some ratio, okay, within 0 to 1. This is called skewness. Similarly, there is a method to calculate the skewness for a quadrilateral element. Okay, this is a triangular quadrilateral. Similarly, 0 is the best element, ideal element. If you have a zero skew, means your cell size compare is fitting actually with the equilateral optimal cell size, right? Then if you have a worst element, then it will be 1. Okay, your optimal cell size minus the sorry, your actual cell size minus the optimal cell size, right? So then there is the cell skewness angle. Okay, you should have a cell, okay, normally that throw the flux away, not to the inside. So the cell angle should be less than skewness angle greater than 90 is a very bad cell, because during the flux computation, if it is more than 90, what will do, the flux computation will come something out of the cell. The cell normal will point out of the cell instead of the cell center. Okay, so then a lot of other things are there. Phase validity, you should not have a chevron cell, means whatever the flux is emitting from the cell, they should be go out. Cell should not be like this, so that here some flux is computing the flux is, instead of going out, some fraction of the flux is coming into the cell. These are kind of cells are a bad cell. We need to avoid this cell, right? So then there is something called volume change. Okay, so then something called chevron cell quality. These are all theoretical things. I am not going into much detail. So now you must have get some idea. So types of cell, and there are some parameter called cell quality measurement, right? So now let's come to the Hansen, see how to mesh that volume mesh. Okay, so this is the cube. So oh, okay, sorry. Yeah, so what we did, we have take the prism layer. So we set the prism layer. Then there is option, we either want pyramidal cell. I explain you what is pyramidal cell over here. Okay, pyramidal cell, that is for the quad to trace transition. Normally, the if you choose this option, this is a quad cell, this is state cell. The solver will generate some quad cell, some state cell, where there will be a transition to fit between quad to tail. It will fill it by pyramid kind of element. This is what this option is telling. Then there is a hex core cell. Hex core cells, basically it will do at the core, it will do the core, the center of the boundary, it will generate some hexahedron element. Everywhere other places it will generate some tetrahedron element. Okay, then there is called something polycell and polyhex core cell. So nowadays, after we can say 2015, okay, most of the solver, they have the capability, commercial safety solver, to do computation over a polycell, because when you do the polycell, the mesh count is drastically decreases, it's dispersive in nature, and solution is more accurate and computational efficient. So that's why most of the computation in the new geometry, they are running on a polycell, new safety software, right? But it's not mandatory. You can still go to the other kind of cell. So let's go to the polycell and hex core polycell. We'll go to the hex core polycell later. Let's go to the polycell. Okay. Once go to the polycell, it will asking you the size field or the geometric. Let's put it default geometric, or you can put it compute. Okay, growth rate, you can change the growth rate factor. If you want your cell to be growth rate to be 1.1 or 1.001, this is the volumetric change ratio. This is the growth rate. This is the maximum cell length. You can put it something. If you want to control 10, based upon the geometry, you can put it, right? This merge cell zones with region means the prism layer, it will create it. and the rest of the volume layer, it will merge it. If you don't put it, the prism layer will be separate zone and the rest of the volume will be separate zone. Now let's apply it, mesh it. Okay. The meshing is going on. You can see 30%, 37%. Mesh is finished. So polyhedra is created. Okay. So let's see. Wait for till it is 100%. Yeah. The volume mesh is generated right now. How to see it? Reset. Let's go over here. Draw all the boundaries. So what earlier we have seen here, you can see the reset. Notice the changes. So now the all the triangular elements, they are combined together to form the poly element. Okay, draw. Now it's a poly element is done. That's not we cannot visible the triangular element because it's now converted to poly. Now this is a volumetric cell, right? So how to see if it is a volumetric cell and oh, sorry. So let's check the quality summary. Okay. The summary is showing the maximum quality is around 0.5. So what is the quality? You can check it or go to auto node move. You can check the quality measure. Here just there is a lot of measure. One is skewness, aspect ratio. I just explained you. Inverse orthogonal is the default quality. So inverse orthogonal, if it is less than 0.9, the mesh is a good mesh. So inverse orthogonal means 1 minus orthogonal quality. Means how orthogonal is your mesh. Ideal mesh is 90-degree orthogonal, and how close your mesh to the orthogonality, that is decided by the factor, orthogonal factor. 1 minus that orthogonal factor is the inverse orthogonal factor. Okay. So now let's see, visualize the mesh. So let's reset. Okay. Again, draw boundary. Mesh is generated. Now see the mesh. Now see the mesh element where to do insert clipping plane. Okay. You can clip either in X limit, Y limit, or Z limit. Any direction you want to see it. Suppose clip it in this direction. Okay. So now this is, you can see its surface elements are only visible. Volumetric elements are not visible, right? Suppose I want to see the volumetric region element, how the mesh is created. Okay, so let's put it draw cell layers. Now you can see how the volumetric element is generated. So we have earlier discussed about the prism layer. If you enlarge it, zoom it, you can see the prism layers, they are generated adjacent to the wall. 1, 2, 3, 4, 5. 5 prism layer we have described. These are generated adjacent to the wall. Then rest of the thing, they are generated the polymeshes. Polyhedral elements are there in the rest of the core. Okay, where we can compute the turbulence. But for the viscous sublayer or the low Reynolds number model, we need a very fine mesh near the uniform mesh near the boundary that we capture to the prism layer, right? So this is the mesh is generated. Okay, let's save it. Okay, file, write mesh. Okay, so this is the qmesh.gz format. There is a option by default h5. The this is the newer format in the Fluent to save the file. Just we put qmesh.gz. The gz is just something to compress the file. File size is not our very high. Cube, we just make it polymesh. Okay, we can save it. Now the mesh is saved. We'll read it next class. We'll use this mesh to set up the Rayleigh-Bernard convection, right? So now next come, suppose we want a hex core polymesh. What to do? First go here, okay, delete. Now what happened? All my volumetric regions are deleted, right? But my surface region will be there. Now earlier you are seeing a polygonal element at the face. Now it's a triangular element. Now let's click. It's the triangular element, right? So now let's come few other surface cleanup operation we'll learn here before going to the hex core polymeshing. Okay, so let's suppose there is some element you feel it's not okay, means the geometry is not closed or there is some bad element or something. In that case, what to do? Okay, there are few options here in the bottom, you can see it. Okay, this is called the node. If you can select a node, this is you can select a edge. Just I in the thing I have explained you the mesh terminology over here. What are the mesh terminology? Edge, node, cells, face, etc. This is something called node. This is something called edge. This is face. This is zone. Okay. This is object. Okay. So let's go to the face selection. Okay. So now I go to the face selection. Then right click on any element over here. Okay. Now suppose I delete it element. I select it and deleted the element. What happened? Escape F2. Okay, so something not correct. The delete option, it's somehow why not showing. No. F2, F7, select everything. So if some element or something is not good or deleted, you can generate this here by selecting the node and generate element kind of thing. If some duplicacy is there, you can delete it. So tomorrow's session, if time permits, I'll show you those things. I need to find out why the delete option is not coming. Something I need to figure it out. Oh, no, sorry. We are in the object draw. Okay. Now mhm. I think you need to reread the mess, but anyway, we'll go to the other option. Okay, so let's, if you want to remesh the particular face, right? I'll tomorrow show you how to clean the pierced face or the face skewed or the face that are not corrected, how to create generate it over here. Maybe tomorrow I'll show you. Suppose you want to remesh the particular faces here, you can go select that edges, then this option I guess interactive edge zone creation. No, this is not the creation, this is some this is the remesh. I don't know why it is showing its thing. Let's read the mesh again. So something is not okay. Import CAD, import CAD. Same thing will into report. Okay, let's see, something is wrong. Let's see. Yeah, done. So let's come over here. These are all the face zone label, mesh object. Okay, so let's see it over here. I need to restart the computer or what? This. Oh. Okay, I will figure it out. There's something wrong in the Fluent. I think we need to reopen or something. So it's not showing some option to me. But anyway, if you want to remesh the model, etc., particular face sizing and all, they're available here. You can go over here, the model. You can go to the model tree model. Then it is sizing. Then something is called scoped, right? Here, if you can come, so globally we have imported the mesh. The minimum size we have put 2, the maximum size we have put 10. Just like that, we have imported it. Suppose some surface we want to refine, some surface we want to make it coarse. Like that, just what you do. So you create a new list, okay? So just hot surface I want to refine, hot refine. Then what is the nature? It's a curvature. The minimum should be 2. So if I want to sorry, coarse, hot refine into coarse. Hot mesh I want to coarse it. So let's say put it 5 or 7 or something element. The maximum element already we have taken 10. So let's put it 5. Okay. This is object modified to the thing. And selection we have phase zone. Okay, which phase? Selection. Suppose not all phase, we want hot phases. Okay, to be coarse one. Compute. Now it is done. Now you can close it. You can go over here. There is option called remesh will be there. Diagnostic match, rename, delete, remesh phases. Now the things are remesh already. Okay, let's see. Find out where is the hot phase. If you can see over here. This is my hot phase. Okay. There's something. This phase is already remeshed. Okay, so this phase is already remeshed, hot phases, right? So if you want to see again remesh it, you can go over here. You can go to scope, the thing, delete the size field. Okay, this hot field just create. Sorry, it was not created later. This was created now. Compute. Okay, the hot phase, the scope was computed. There is no error. Okay, close it. Then come over here. Remesh phase. Okay, the face is remeshed. Go and visualize it, draw it. Now you can see the elements are big in size compared to this size. Okay, if you want to see further big element, go sizing, scope, then you delete the size field, come to the hot phase. Instead of minimum 5, you make instead of something 10, maximum something you make it around 50. Like that, if you want to modify, this will give you some the maximum size should not be greater than global maximum size. So global maximum, it will be automatically 10 to 50. Okay, then it will go for the compute. Now size field is somewhat done. Then come, you can do it again, a remesh over here. This is just for surface remeshing. Okay, reset. Now you can go and visualize. Okay, so this is where you can do the surface remeshing thing. Okay, you can control a lot of surface. And then let's come to the volume option. Again, already we have done it, automate. It is scoped and all. Okay, so now let's go scope. Okay, sorry. So the region is not computed. First you compute it region. Region is computed. Let's make it fluid. Change type to fluid. Okay, if after computation of the region, if you are modifying some other thing or remeshing, you just need to update it. Update. Okay, no problem. Mesh is updating. Then you come for the auto mesh. There is a scope. Already we have said the boundary, hot wall, cold wall, all those things are scoped. Okay, this is already generated, scoped. Now instead of the polymesh, we'll come for the hex core polymesh. So then come to the hex core polymesh, it will ask for the peel layer. This peel layer is nothing but this layer that the transition between the polyhedral element and the hex core element occur. This is not minimum, it's 1. You can increase it to 2, 3. It will best give you very good transition. Okay, but again 2 to 3 layer is okay for the peel layer transition. Then merge cell option, apply, message. Oh, something wrong. Apply. Yes. See, meshing started, volume meshing 25%, 20, 30, 50. 100%. The volume meshing is now done. Inverse orthogonal quality. Check as a default quality criteria. Reset. Now, if I go over here, I can see these are my polyhedral cells are formed at the surfaces. Okay, I want to see the interior. Okay, go to the clip plane. Okay, now for the to see the visualize the interior, let's change the click it. So, yeah, yes. Let's draw cells in layer. Now you can see compared to the poly thing, what will happen? The poly mesh is formed somewhere at the surface, right? Then there is a prism layer. Okay, that trim the polymesh to form to take the account of the viscous sublayer in the vicinity of the solid walls. Then there is peel layer. We have put 2 or 3 peel layer of the poly element, right? Then at the core, far away from the solid boundary, this mesh is completely hexahedral. Okay, the computation is normally very fast in the hexahedral because these are the ideal cell, right? The computation is uh, relatively compared to the poly hex in the hex core hex cell, the computation is fast, right? So away from the boundary, solid boundary, the mm, volume elements are hexahedral in nature. Okay, and near the solid boundary it's polyhedral in nature, right? So you can say, so now we can see now the inverse orthogonal quality. Let's check the summary. If you go to the summary, it will show you, yeah, it's 0.48. It is acceptable. The total cell count is how much? 1,39,748, right? It's around 0.1 million. Now we can save it. Okay, done. So far any doubts? So far any doubts?
If anyone have doubts, you can directly ask the expert.
We can go further. If you have any doubts, please ask here so that I can clarify your doubts. If you have all things available with you, any doubts. So I will go again now to the space claim, and I will show you some other option in the space claim. Then again, we'll come to the Fluent Mesa. So if you have any doubts, you can please feel free to ask me.
So I have a doubt, sir.
Yes. Your name, please. Can you switch on the video? I can see.
I'm Saravana Kumar.
Okay.
When the finer is the mesh, the accuracy is more, but at the same time, computation time is more.
Yes.
So is there any optimum level of accurate mesh size?
Yeah, that's why you do the grid independent study. It's again the heuristic approach. You have to adapt it. So you have to prepare a mesh, do the computation, then refine the mesh. You have to do the computation. You have to check if the results is changing or not. If the result is no more changing, then you can increase the size and check if result is changing or not. So you have to bring your mesh to such a level that refining the mesh from that level further is not affecting the output, the results, right? So that is the mesh or the grid independent study. So anything refinement beyond the optimal level will cost you the computational expensiveness, but it will not give you any advantages in terms of the solution accuracy. But if you make the mesh too coarse, you will get a very bad result, right? That's why we do the mesh independent study. So where we do the prepare 3-4 kind of meshes for a particular geometry and do the testing. And for industry, for a practical geometry, there is some thumb rule is set what should be the maximum element size, etc. Because similar geometry will work in a repeated nature. So every time we don't do the mesh independent study, we do it for once or twice for a standard geometry, then it's a standard practice for us to the what should be the fast layer height for the turbulence correction, what should the total number of layers, what should be the polyhedral element size. This will be automatically in the workflow, it will be created.
So it seems that we have to do a number of trials and come to a conclusion.
Yes. You have to prepare a number of mesh and do the computation to know which mesh is good.
Okay, sir. Thank you.
Any other doubts from participant side?
Hello, sir. This is Dr. Venkatesh Ramani.
Can you switch on your video? I can see who is
This is
speaking.
Dr. Venkatesh Ramani from
Okay.
BMS Engineering. Grid independent study is one part, but the type of cell to select for a particular problem, is there any criteria for it, sir? Like for boundary layer conception, what kind of type of cell I am asking? Is there any criteria so that we are going to get the optimum results in a less time? Is there any
Type of cell, I don't understand you. Type of cell, already I have shown you the polycell, hex core polycell, Tate cell, hexahedral cell. Means what exactly?
For complex physics or complex geometry, no?
Uh,
It is difficult to maintain a kind of a particular type of cells. Again, it will be a combination. So, is there any rule that if suppose if it is a boundary layer concept problem we have, then for that zone, if I can maintain a proper kind of cell, and again we have interface to other sides, no, like in free state kind of things. So that directly I can apply such cells to those physics. Is there any
no, for the boundary layer concept, already I have shown you to develop a prism layer. In the vicinity of the solid wall, we are already developing a uniform prism layer.
No, sir.
To accommodate that.
Boundary layer, not necessarily boundary layer. My point is there any thumb rule key, a particular problem we have to select the hexa, or a particular problem we have to use a particular kind of cells? Is there
so far, there is not any such criteria I have came across. So now in the modern days, after 2014 or 15, most of the commercial solver user, they are using the polycell or hex core polycell. The error is minimum in the hex core cell or hex core polycell, but the cell count is high, but the computation is very fast. So the TED cell and other cell, they are almost absolute nowadays for the industrial computation or even if the research computation, unless until you have some old work which you need to validate on the TED cell, it is not recommended. And similarly, some thumb rule, I don't know, maybe for some multi-phase flow viewer kind of thing, if your aspect ratio is more than your something around 30 or 40, somewhere our results are diverging. Again, it's based upon the problem to problem, the criteria you have to define. But so far the polycell is or the hex core poly, it is a kind of widely used thing. So far any porous zone, multi-phase, every solve problem you can solve with this poly and hex core poly domain, sorry, poly volume element.
Okay, sir. Thank you.
So any other question?
Sir, Mr. Priyesh Kumar has asked one doubt.
So it's not visible. Your video is not visible. Can you switch on the video, or you can? Okay, tell me. Ask me the doubt.
Mr. Priyesh has asked that how we select mesh element type for a specific geometry.
How we select a mesh element type specific geometry? So far when you are doing the surface meshing, everything comes under the triangular meshes, right? So then already I have shown you, once you have the triangular meshes, here during the auto meshing option, okay, let's delete me. During the auto meshing option, it is showing the option for poly hex core. Poly, suppose I want the only TET meshing. Okay, let's see. Geometric, the if you have the option TET meshing, it's a non-conformal. If you have interface and all, it will show it. Okay, let's go for the TET meshing. See how much time it is taking compared to the polycell. It is taking long time for the meshing. Okay, so and you can choose over here the TET, poly hex core or the poly hex core. You have the option over here to choose it. Once you choose the hex core, it will add you the ask you for the option quad to TET transition. Now it has only TET, so it has prepare wherever is there. It will not find the interface. It will make it non-conformal. So non-conformal means the surface element in both sides of the interface are different thing. So I think it is a heavy overdose or something. So it's generating. Laptop is getting hang kind of thing. Anyway.
Hello, sir.
Yes.
Sir, so out of these four types which you just said, so which one is the best? How to decide?
Then there is not any hard and fast thumb rule choosing the best one, right? So normally in the modern days, as I told, polymesh is widely used for many problems, right? So and
for
hex core poly, I found it again from people from acoustic and other things. They are also using hex core poly. This hex core and TET is kind of old meshes. Last before 2014-15, people used to use it. Then the poly and the concept of poly and poly hex core meshes came. So I cannot tell which is the best mesh. Even if you solve the same CFD problem in four kind of meshes, they're supposed to give you the same result. If Polys give you different result and TET is giving you different result, then there is no meaning of doing the computation, right? The entire physics is wrong. So that is not the cases. irrespective of the meshes, in which meshes you will solve, they're supposed to give you the same result. But the thing is that sometimes the poly or the hex core poly, they are computationally efficient, they are dispersive in nature. The cell count is minimum, the efficiency is high, computation time is low. So that's why they use the poly or the hex core poly. You can see it was taking few seconds to meshing, where TET mesh is taking long time to do the mesh. Maybe it is partitioning first to the parallel parts and all. But again, that's the thing where it depends upon the individual which mesh he prefers.
Okay, sir. Thank you, sir.
Let's restart it. I think something is taking time. Let's kill the Fluent. Let's kill the Fluent. Okay, Fluent is killed. So any other question? We'll go to the next geometry and show it something, some new aspects, or any other questions are there? Always prefer quad mesh. This is surface element. This is normally when we are doing the in-house code development today. So we can have quad element, we can generate, but it's a very complex geometry. It's not always possible to generate a quad element. So normally the triangular elements are created as of the Delaunay triangulation. So you can learn more theory about it. It's called Delaunay triangulation. So any surface you give it, the break into the number of triangles as a surface mesh. Then they combine those things to form the quad. If it fails to form the quad, it's some triangle and quad mixture, it is unstructured mesh. Otherwise, some triangle they'll mix it to form the surface poly kind of thing. Any other queries? Oh, this also hangs out. Space claim not responding. Okay, let's start it again. I'll show you some other kind of meshes also. I'll show you in the workbench, the old version, because here in the Fluent Mesa, whatever the meshing we are doing, this is for the fluid specific. But earlier people in a common platform, they used to mesh it, the workbench. Okay, something partition directory error. So there they used to prepare mesh for the structure problem, there the fluid problem. We'll go there and see it. Okay, file, open design. Oh. So cubes and pipes, this is the thing. Okay, so let's close this. Okay, this is cubes and pipes. Okay, so what is the thing? Okay, so before taking this thing to the Fluent, okay, if you want a conformal mesh, okay, there is no duplication or something, because here if you look, this is one zone is there. Okay, this is a other zone is there. They are joining at a particular surfaces, right? This surface is the common, and here the mesh needs to be single. If you as whole as the present state, the geometry exists. If you take this to the Fluent meshing, you will get a duplicate element, because the mesher will 2 times do the meshing at the interface. That we need to avoid. How to do that? So let's pick the geometry. There is something called workbench. Okay, go. Then something called share. It will find out the faces that are sharing, right? So once they will share it, you will find they are in the pink color. Now the geometry is shared, means there will be no duplication. Okay, only one geometry will be there, that will be imported. So let's save it. Now we have do the workbench. So again, if you want to unshare it, unshare, select. Now everything is unshared. Okay, if you want to share it, share. This will show you two faces to share. Select, things are shared. After it's sharing, everything will be pink color. If some duplicate or something will be there, it will be in yellow color. If some piercing face or something will be there, it will be in yellow color. You need to modify your geometry, right? Let's come Fluent Meso. Meshing, let's do it serial meshing. Something is problem is coming parallel, maybe the shortage of RAM or anything. Let's do it serial meshing. Start. Okay. So now I save it. Okay. Now import it. Geometry. File. Import CAD. Cubes and pipes. Okay. CFD surface mesh. Put something around 2. Something maximum around 20. Proximity, number of cells per gap, you can put it 2 or something. Okay. Input. Okay. So now the mesh is imported over here. Let's see. Again, go to the mesh object, cubes and pipe. Okay. Visualize, draw. Just put it a feet. Yeah. You can see. Okay. This element is created. There are, you can see multiple kind of thing. One is yellow color. Yellow color means this edge is shared by two elements. Okay, this edge is shared by two elements, so that's why it is not showing any color. If this edge is particularly shared by more than two elements, it is yellow, means it is called T edge. Okay, it's a T-shaped thing. Okay, so this is this edge. Okay, is shared by the element that I can go somewhere, hide somewhere. You can see. Now I can see delete and all. Earlier it was not showing, some problem was there. Now I can go and hide it. You can see if you come. Okay, this face is shared by three elements. One element this side, one element this side, one element this side. That's why it is showing yellow color. So if you go for the multi, or it's called multiface. If you switch off the multiface, it will not show you. If you switch on the multiface, it will come, right? So this is called the yellow element. Suppose there is an option called free face, means if there is no connectivity is missing, this will come as a free face. Let's go over here. Okay, now I deleted some element. Now we see this is highlighted in the cyan color. Okay, somewhere here I have deleted one more faces. This will be shown in the cyan color. This is what this is means free face. So how to, if here I have deleted, so that's why I know there is a face is missing. If I have not deleted, by default the geometry has some problem and some face error comes during the face meshing and some elements are not created. That time it's a possibility that it will show you the free face. How to diagnose those things? Let's go here. Okay, then there is an option called diagnostic, connectivity quality. Okay, then there is an option called free face, right? Mark it, how many free face. There are all total 6 free face is showing. Then what to do? Go to the first free face. Let's go. Okay, this is showing this is the first free face. It is asking what next to do. Okay, so F2 means deselect everything. Oh, something. So what I need to do, suppose I want to delete these free faces. Okay, I can go and delete it. Now the more free faces is created. So how to fix it? Go to find an edge. Okay, select any edge. Then there is an option called generate, create. This is option called create. Okay, just a second. I just separate each option. Okay, create, geometry, create. Yes, you can see something is created, right? So, but still it is showing free faces because it's a new geometric object is created. Okay, so to avoid that one, okay, next go mark how many 9 free faces it is showing. So this is again showing there is a number of free faces. How to stitch those free faces? So I can go and delete them simply. Okay, so then again select it, split swap, create new object, no, add to object, geometrical object, wall, create. Now you can see the free face is gone. Okay, but some new face with some new name is created, right? So similarly, if you come here, mark the free face is now 3. You can go over here, you can select, you can delete it, those things. Now how to fill this? Go over here, add object. Now it's created, right? So the thing is that there are a lot of unreferenced places now created over here, face zone. So these things patch that is created. So if you want, we can merge it finally. This is not a very big deal. So how to do that? Go to boundary. Okay. This is which face? We can come which face this is. This is 02 chamber. This face name is 02 chamber. Okay, so what you will do? So now reset it. The best way to reset it, draw it. So we want to merge this face name with this face. Okay, because these are element, these are not only element, these are different faces. That's why these are visible in different color. We want to merge it. Go to boundary, there is option manage, right? Then there is an option called merge. Okay, then is a option called merge. Then there is a alphabetical order, there is a larger area. Just choose larger area. Then you have to select those boundary which you want to merge. Which are the boundary? This boundary I have chosen, this is for merging. This boundary I have chosen for merging. This boundary I have chosen for merging. Then go for apply. Now you can see all are my one boundary, right? There is no separate patch kind of thing. Okay, so again, if you untick this option separate, okay, I untick the option separate. Now if I go, okay, and delete some element over here, okay, some element over here. Now see number of faces. I want to create the sorry, I want to patch or the fill this missing element. So just go over here, select any edges, okay, fill. Now it is fill. It will not ask you to form a separate region, right? Just untick it like that. There are a lot of other options to create by holding the creating the nodes, putting the nodes. You can create it, and other lot of other things are created here. You can also, if you forget to rename something on the workbench, here also you can rename those things. Manage, here there is option called rename. You can change the rename, you can change the type. By default it is wall, so if you want to make it change the type, you can also change the type. A lot of other options are there, right? So let's close it. Now it's a TS. Now focus on the volume extraction. Okay, so compute. Now how many zones is supposed to be extracted here? 3 zones, right? One is this pipe inlet zone, one is this chamber, one is the outlet zone. See, 3 pipes are generated. Okay, so one draw. This is suppose my outlet. Here I can rename it. sorry, this is my inlet. This is my inlet pipe. Okay, this is draw. This is my chamber. I can rename those things over here. So these are now my 3 regions. Okay, I can simultaneously view all. Okay, now these are in, what is the type? They are in by default solid. What I need to do to make it the type, make it fluid. Right now they are all are fluid. Suppose I don't want to mesh a particular section, then I can option to add it as a dead, means it will not do further volume meshing of it. You can put it as a dead. Okay, so now 3 sections are generated. Let's go and generate some polymesh on it. So again the same procedure, go auto mesh. Okay, then cube pipes, the object is there. If you want some scope prism, here we can go. Then we can wall prism, any name you can give. Then aspect ratio, number of layer 5, then you can put the growth rate, etc. The growth on, so here you check it, selected phase zone, right? I want prism everywhere except at the inlet and outlet. This is the boundary condition. Oh, sorry. That's why I excluded inlet and outlet. Everywhere else I want the prism layer to be grouped. So now growth option, create. Now the wall prism created, close. Now I want poly mesh in this region, so I just do it compute. Okay, so I do some computation. Merge cell zone condition, it will merge the thing. Apply. Now just give meshing. See how fast the poly mesh is. Now polymesh is created. Okay, close. Now you can see the tape mesh because it's the surface mesh you are there. To see the polymesh, what you will do, reset over here, go over here, draw. Now you can see the polymesh. So you can see the boundary. These are the inlet and outlet boundary. So here I don't want to growth the prism layer. Prism layer I only want to growth across the solid walls, because boundary, these are something fluid in which I don't want. So I just grow the prism layer across the solid wall. You can see how uniformly they are generated and how the uniformly they are stretching. You can control the stretching factor. You can control the first layer thickness based upon your wall y plus value or wall shear. You can control those things. Now you can see the sectional views. Okay, so suppose this, I want to draw the cell. Now I can see the sectional views. I can see the prism layer across the wall over here, the poly mesh in the center over here. Okay, so I can see this is the mesh generated in the pipe, right? So a lot of functionality is there. You can play around to see it. So you can change the direction. Okay, this is in this direction. If you change it, you can see this is how my interface looks like. I just told you, if you share the topology here, the share topology, we did it over here by workbench meshing. So after sharing the topology, what will happen? This is a conformal mesh. What is conformal mesh? This is the interface, right? If the in the left side and right side interface, they share the same mesh definition, the number of grids in the left side of the mesh and the right side of the mesh, they are the same. This is called conformal interface. If the number of grids in the left side and right side, they keeps on changing. Here suppose there is a 200 elements, this side there is a 150 elements, then this is called non-conformal interface. In case of the non-conformal interface, during the flux computation or sharing of the property, what the thing they do, the solver do, they do some interpolation. That interpolation generates some error. It's again nominal, but there to have maximum number of accuracy, we should have the conformal interface. Okay, suppose I don't want this prism layer across this interface. Okay, I don't know, so this interface has some name. I don't want prism layer across this interface because I just want prism layer across my solid geometry, not at the interface. What I need to do, I need to exclude my interface from the prism layer setup. So how to do that? Let's delete the volume mesh. Where is that? Sorry, not here. Yeah, delete all. Now I deleted. Okay, so let's come automesh. Here you go to prism layer scope, you go to the phase zone. Okay, so normally the interface they share between two geometry. Okay, so that comes with the names that shares by two geometry. Here are the interface. Okay, so these are the interfaces. You can easily trace it out. One pipe. These are the interfaces, right? So we can choose it interfaces. Okay, so here we choose not to provide the prism layer. Okay, modify, close, apply, mesh. Close, done. The volume mesh is done. Reset it. Let's visualize the volume mesh. Oh, I have the selection cutting. Good. Now you can see, now when I excluded, something wrong. So I excluded everything, I guess, from the prism layer. So prism layer I cannot see anywhere, right? I cannot see my prism layer anywhere because something I excluded, I guess. So to do that, how to do again? Just reset, go, delete all. So here volume layer, sorry, here automesh, automesh, prism layer set, wall prism. Okay, so let's see which are the interface, to how to know which are the interface or nothing, which faces. Draw, this is the faces where I need prism. This is the face where I need prism. Yeah, these are my boundary faces. This is the face where I need prism. This is the face where I need prism. Yeah, yes. This is the face where I need prism. No, this is the interface. I don't need any prism layer over here. This is the face I need prism. Draw. Yes, I need prism over here. You can visualize a kind of, this is a kind of visualization you can do to see where you need, where you don't need. So this is a place where I need visualize the prism. Draw. No, this is a interface. So this is a place where I need to generate my prism. Okay, fine. These are the things where I need to generate my prism layer. These are the interface. These are the inlet boundary condition where I don't need to generate the prism layer. So let's put okay. Then modify. Always remember after any changes, try to modify it. Okay. So now, oh, why, what happened? Okay, this now available. Let's see, everything okay? Draw it. Yeah, these are the faces. I need to interpret, generate the prism. Now it's available. So modify. Okay, close. So apply mesh. Okay, the volume meshing is done. So each zone wise it is showing the quality. If you come, it is showing the quality. Each zone, which zone is good quality, which zone has bad quality, zone wise cell count, everything will get it over here. Let's see we got the desired effect or not. Okay, let's come to the reset, draw all boundaries, then okay, from this angle. Okay, just see by this thing. Okay, what we did, we just avoided the interface creation at the junction, right? Sorry, the prism layer creation at the interface. But at the same time, we generate additional problem. Once we avoid prism layer creation at the interface, the additional problem what we face, you can see the prism layer started collapsing. Here the 5-layer prism layer, they gradually become 3 layer, 2 layer, 1 layer. Somehow prism layer collapse will be here. So what will happen when you do computation in this mesh, right? When you do computation in this mesh, so what will happen? There is a possibility that the turbulence quantity computation will be give error at this point of, at this sharp corner, because here the interfaces are collapsing. Okay, deliberately I did this to show you. So you need to take care, even if generating the interface across the generating the prism across the interface, they're a little bit computationally expensive. They're, I mean, increasing the cell count, but it is helpful for you so that there is not any place where the deliberately error is coming. Just like prism layer collapse, here you will get turbulent kinetic energy high, and if you are doing the temperature, you will get a very unnatural hotspot kind of thing over here. If the turbulent flux heat flux computation is not okay, so to avoid that thing, there is a lot of way to do that. Normally in the geometric level, we do some dumbbell shape kind of thing, so the prism layer should not collapse here. It will collapse somewhere here inside, so that is fine. So otherwise we just generate the prism layer across the interface so that it's okay. There is no problem in the computation that, but additionally some mesh count will be increases everywhere. You can see how the uniform prism layer is coming, 5 layer. Okay, they are gradually collapsing at the corner. To avoid that thing, we can either create a dumbbell or generate the prism layer, allow the prism layer to growth across the interface kind of thing. Okay, so this is again we came to the end of the today's session. I guess we are already running short of time, so I like to stop here presentation and ask if there is any more question that I can address from today's lecture, through today's lecture.
Participants can raise their hands or put it in the chat box if you have any questions.
Any questions?
Sofan sir is Deva here.
Yes.
Can you tell me something about the refinement of the meshes? Maybe we start with the coarse mesh always, and we try to refine it.
Okay.
What is maybe there's a limit for the going for refinement? So can you discuss on that particular thing?
So I could not understand your question again. Refinement limit means?
We take a geometry and we'll start with a very coarse mesh.
Okay.
Okay, then we start refining it, and there's a limit for us to go for refinement.
There is no limit. There is no limit for you to go to refinement. There is a limit of hardware, means how much million mesh count your hardware can handle. Suppose means on an average in a thumb rule, for 1 GB memory is required to handle 1 million mesh count. Suppose you have doing a LES simulation, you have 60 million mesh count or 80 million mesh count. You need a supercomputer allocating you at least 80 GB of memory, right? So as long as memory is available to you, there is no problem in limitation of the refinement of the mesh. If you solving some turbulence problem in a large AD simulation, you need a very fine mesh. So that time you need to refine. First you need to solve the RANs, K omega or K epsilon model, then find out the area from the RANs result which needs refinement to give you the turbulence, means the at least the spectrum, Kolmogorov spectrum. So 80% of the spectral energy need to be resolved within your mesh, and 20% you need to model it at subgrid scale. So you need to refine those things. There is not such limitation is there. The limitation only comes in terms of the hardware, means you are doing it using a supercomputer or hardware. So just like morning I was discussing with a professor Tapan Sengupta from Aerospace Department IIT Kanpur. So in ISC Bangalore Supercomputer Center, he was running a CFD problem with 22,000, around 20,000 core machine, 20,000 core machine. The problem is running for 6 months of time. It's some 3D computation they are doing. It is running for 6 months of time, one CFD problem with around 20,000 core. It's a we can say in crores, around 3 crores or 5 crores. How I say it's a 10 million Indian rupees. Sorry, 10 million. It's around 30 million Indian currency. The ISA is charging for doing those kind of simulation around. So it's up to you how much hardware you can afford and what level of accuracy you need it for your solution. Accordingly, you can refine. There is not such limit is there.
Okay. My second question is, sometimes we try to couple the meshes actually. Maybe I have two different geometries. One maybe having maybe a triangular, maybe a quad mesh, another one maybe I may be having some kind of a triangular geometry. So usually we end up this particular problem where the meshes are not properly attached and all. So is there any something rule where we can check and we can identify this kind of problem and we can look into that?
The mesh is always need to be attached. Otherwise, how will do computation? If the mesh is not attached, you will get an error in the Fluent solver. The mesh is always attached. Once you do the meshing in the Fluent mesher, you'll always get the conformal kind of thing meshing, and everything you will find the mesh is attached. So either you can choose here in the Fluent mesher poly meshing, hex core poly meshing, or tate meshing. You cannot have option to choose a tate for a part and hex for a part. But again, in the workbench, that functionality is still there. You can adjust something around what you call sweep mesh, somewhere poly mesh, those kind of thing. But again, doing that thing is not something you have a connectivity issue. So define the mesh is not something you are doing magic, right? These are some mathematical function they are using to generate the mesh. So define some logical function, something that guarantee you a good mesh. So don't do some out of the box thing. So the mesh fails normally most of the time. So but in the Fluent mesher, you will not face that issue. And why you need a different kind of meshes, that I don't understand. Why you need a particular state mesh in one part, hex mesh in other part? Is there any reason? So it's not polymesh is capable of doing all those things. So normally, whenever the requirement for uniform mesh or something in the old days around 2005 to 2010 era, then the extrusion kind of thing, they use the sweep mesh. Then the other part, they're using the tate mesh kind of thing. Now, even if the polymesh is computationally so expensive, sorry, effective, so they are using it for everywhere.
Thank you, sir. Thank you.
Yes.
Any other questions?
Any next questions?
I think there are no questions.
Yeah, we are 15 minutes already
Yes, sir.
taken more.
Please
So.
unshare the screen, sir. You want to take a group photo?
You need a very good visualization monitor for the meshing. So yesterday I was in the office, so I have a big monitor there. Everything was visualized. When I seeing it the laptop screen, it's a bit difficult. Anyway, we'll continue.
Sir, please unshare the screen, sir.
Okay.
So all of you, please turn on your video. Taking the attendance, please, and turn on the video. All of you, please. Okay, thank you.
Okay. Thank you. See you tomorrow. We'll give some information about short information about workbench meshing. I may not be have time to complete all the functionality of the workbench meshing, but give some short information. Then we'll mesh that pump. I got some email from someone. They're interested in the turbo machinery thing. If possible, we'll mesh that turbo machinery geometry, and we'll go for the force convection setup tomorrow for the turbo machinery. The turbulent force convection setup in the Fluent turbo machinery, we can go tomorrow.
Thank you, sir. So tomorrow we have your session at 8 a.m. According to your CE standard times.
It's a big challenge in the early morning. It's okay. Okay, I'll come at 8 a.m. No
Yes,
issue.
sir. Thank you, sir. Thank you, sir. And also I thank all the participants for your active participation. Thank you, sir.
Okay.
Okay. And
Have a
now,
nice time. Bye-bye.
thank
Anything
you, sir.
else?
Participants, we have our tomorrow's session at 9:30. Bye.